This is video 2 covering chapter 4, looking at experiments, the outcomes of experiments, and attaching probabilities to the outcome of experiments. When we assign probabilities to the outcome of an experiment, those outcomes defining the sample space, there are two basic rules which must be followed. This slide presents the first rule, which basically just says that an experiment can lead to an outcome, which we denote here by E subscript I, where I is the ith possible outcome. P stands for probability, so the formula says that the probability of any particular outcome of an experiment must be between 0 and 1. Really, all we're saying here is that negative probabilities don't make sense, and we can't be more than 100% sure that anything will happen. The second basic rule for assigning probabilities is that once we've defined the probability of each event in the sample space, and we add up all of those probabilities, they will add up to be 1 or 100%. Basically, all we're saying with rule number 2 is that we're 100% sure that our experiment will lead to some outcome. Now that we have these basic rules, which will always be useful in assigning probabilities, we can talk about the three basic methods of assigning probabilities. The first method is known as the classical method, or the equally likely outcomes method. Assigning probabilities based on this method often makes intuitive sense. For example, if I roll dice, there are 6 sides, so each outcome, 1, 2, 3, etc. through 6, should occur with a 1/6 probability. If I flip a coin, I might assign a probability of 50% to heads and 50% to tails. In both cases, note that our two rules of assigning probability is satisfied. In the case of flipping a coin, 0.5 for heads and 0.5 for tails, we have probabilities that are between 0 and 1, and the sum of the two probabilities, 0.5 plus 0.5, is equal to 1. Suppose, however, that we're flipping a coin, and we're not sure that we have a fair coin. We might be unwilling to assign equally likely probabilities to heads and tails. In this case, we might flip the coin a large number of times and observe the frequency with which we see heads and the frequency with which we see tails. If we were to see a frequency of heads of 60% and tails of 40%, then we might conclude that the coin is weighted unfairly towards heads and assign the probabilities accordingly. In many cases, particularly in business, we will come up against situations where neither the classical method really makes sense and the relative frequency method is unavailable to us. If we're in a situation where we don't think every outcome is equally likely, and we don't have enough historical data and experimentation is impossible, we'll have to attach subjective probabilities, which will be based on our best judgment. The nice thing about statistics, and in particular Bayesian statistics, is we have well-defined rules for updating our probabilities based on information as that information becomes available. Some basic relationships in probability theory that I want to cover in this video are the complement of an event, the union of two events, and when you see the word union, you should think of the addition operation, the intersection of two events, and when you see the word intersection, you should think of multiplication. I would also like to discuss independent events and mutually exclusive events. Here's a basic introduction to Venn diagrams and the way that we're going to use Venn diagrams to discuss the sample space and events. The sample space is represented by the entire white rectangular area. You can think of that as 100%. Event A is the event that's enclosed in this circle. Anything that's not in this circle is not included in event A, and we call that A's complement, or A superscript C. According to our rules of probability, it should be clear that the probability that A occurs plus the probability that A does not occur is equal to 1. Now for something more interesting. Let's look at the case where there are two possible outcomes from our experiment. Event A and event B. So event A can occur, event B can occur, They can both occur simultaneously, or neither event can occur. This is represented in a Venn diagram by two circles that intersect each other, event A being the left-hand circle and event B being the right-hand circle. The fact that they overlap suggests that the two events can occur simultaneously. The intersection operator looks like an upside-down U. We can state that the probability of A's intersection with B is equal to the probability of A times the probability of B given A. Recall that in the previous slide, when I suggested that when you see the intersection of two events, you should think about multiplication, that's what we have here. The probability of A intersection B is the probability of A multiplied by another probability, which is the probability that B occurs conditional on A having occurred. We will talk more about conditional probability a few slides from now. But here, note also that we state that the probability of A intersection with B is equivalent to saying the probability of A and B occurring. In other words, the probability of the two events occurring at the same time. Here's an example. Suppose we have 3 boxes. Box X has 10 light bulbs. 4 of those light bulbs are defective. Box Y has 6 light bulbs. 1 of those light bulbs is defective. And finally, we have a third box, Box Z. Box Z has 8 light bulbs and 3 are defective. We're going to run a 2-step experiment. In the first step, we're going to randomly select a box. That means we're going to select each box with a probability of 1/3. Notice that this satisfies our 2 rules of assigning probabilities. Since 1/3 is between 0 and 1, and we have 3 boxes, and 1/3 plus 1/3 plus 1/3 is equal to 1. Once we've selected the box, we'll select a bulb, and then we'll test to see whether or not that bulb is defective or non-defective. Here's a tree diagram of our experiment. First step, you can see, is to select the box. This happens with a 1/3 probability each. We then randomly select a light bulb from the box, and if we've selected box X, we have a 2/5 probability of getting a light bulb which is defective. I've denoted that here by D, or a 3/5 probability of selecting a light bulb that is not defective, and I've abbreviated that by ND. What you can see is that the appropriate formula for calculating the probability of selecting a box and finding a defective or non-defective light bulb follows exactly the formula that we covered on the previous page. In other words, if I want to know the probability of selecting box X and finding a defective light bulb, I will take the probability of selecting box X, which is 1/3, and I will multiply it by the probability of finding a defective light bulb in box X, or in other words, conditional on having selected box X, and that is 2/5. So the probability of selecting box X and finding a defect is equal to 0.13. Likewise for all of the other entries in my tree diagram. We call these probabilities at the end of the decision tree joint probabilities. When we talk about contingency tables or pivot tables, as we did in Module 1, these are the probabilities that show up in the middle of the contingency table. You will also recall that in a contingency or pivot table, we have margins. One of the margins is always already represented in this tree diagram. These probabilities of 1/3 are marginal probabilities of selecting the boxes. In order to calculate the marginal probabilities associated with defective and non-defective items, we will have to sum across the various entries in the second step of our 2-step experiment. That will become clear in the next slide when I show you this information in a pivot table or in a contingency table. Before we get there, let's do one formal calculation with all of the symbols and the formulas from the previous slide. So here what we're looking at is the probability that we select box Y and, so we have an intersection, so we read that as an and the probability of finding a non-defective light bulb. In order to do so, we just work our way from the left to the right in the decision tree, and we find the probability of selecting box Y. That is 1/3. Then we multiply that by the probability of not finding a defect when we select box Y. That's a conditional probability. So we've already selected box Y, and the probability of not finding a defect conditional on selecting box Y, we can see is equal to 5/6. So the answer is 1/3 times 5/6, which is equal to 0.28. So there is a 28% probability of selecting box Y and finding no defect. Now we're going to switch to our first checkpoint question. In this video, I would like to have you open up a document called Chapter 4 Video 2 Worksheet.pdf. The response questions for moving through this video lecture are contained in this PDF file along with background information which I expect you to read and complete. There are a number of different tables to fill in and a number of different questions which walk you through the material that we're covering in this lecture. You should fully work through this exercise in answering all of the checkpoint questions. If you can successfully work through all of these exercises and get the right answers to the checkpoint questions, you can rest assured that you're following along with the material successfully. Our next topic is the union of two events. The union of two events A and B is the event that contains all the sample points that are both in A and B. So the way that we read the union, and it's easy to remember the symbol for a union because it looks like a U, is we read that not as the probability of A and B happening, but the probability of A or B. So you should remember the word or every time you see the union symbol. So the probability of A's union with B is the probability that event A happens or the probability that B happens. This is what's called the addition rule. We take the marginal probability that A happens, remember the margins from the table and the margins from the tree diagram, plus the probability that event B happens. That's the sum of the area inside event A in my Venn diagram and the area inside event B in my Venn diagram. However, if I add those two areas together, I'm adding in the overlapped area twice. That's why I have this term tagged onto the end that subtracts out the probability of A and B, or the intersection between the two events. If you forget to subtract out the probability of A and B, you will be counting the intersection of the two events twice, and you will not get the right answer. Here's an example. Again, coming back to our box and light bulb two-step experiment. Here's the experiment. Again, we're selecting the box first with a 1/3 probability each, and we have conditional probabilities of defective and non-defective depending on the box that we actually pick. What I'm looking for here is the probability of A and B. So I could answer a question like, what is the probability that I select box X or I get a defect? So with the union, the key word is or, and we want the addition rule. In order to see how this works, it's easiest to take the information that's here and put it into a pivot table. So on the next slide, I have a pivot table where all the probabilities are pulled from the previous slide. The numbers that show up in the middle of the table are again what I have called a number of times now the joint probabilities. That is the probability, for example, of selecting box X and finding a defect, which would be equal to 0.13. That is the probability of a defect conditional on having selected box X. Of course, the probability of selecting box X and finding no defect, the probability of A and B here, is equal to 0.2, etc. What I have at the edges of the table are once again the margins. I find the margins by adding up either across the rows or down the columns. When I add up down the columns, I get the probability of defect or non-defect. Therefore, I have the marginal distribution of defect and non-defect. If I add up across the rows, I get the marginal distribution of box, which box I've selected. And that, of course, you already know is equal to a third for each box. If I add up the marginal distributions, again, just as if I add up all of the entries that are in the middle of the table, I get the answer of 1, or 100%. Now let's apply the addition rule. Let's calculate the probability of selecting box Z, and here we have the union, so I need to read that as or finding no defect. So this is the probability of selecting box Z or finding no defect. The addition rule says take the marginal probability of selecting the box Z, which is equal to 1/3, add to that the marginal probability of not finding a defect. We found that by summing up all the no defect probabilities in the table in this column. So that is equal to 0.69. But we've counted the area 0.21 twice, the probability of selecting Z and finding no defect. So we need to subtract that out once. That's why I subtract out the 0.21. The answer is 0.81, or 81%. So there's an 81% probability of selecting box Z or finding no defect. Conditional probability. The probability of one event given another event has occurred is called a conditional probability. We've actually already talked about conditional probability. The conditional probability of A given B, for example, is denoted the probability of A conditional on B, or given that B has occurred, and we use the vertical line inside of the probability operator in order to signify that conditional probability. Here's a Venn diagram of conditional probability. To calculate conditional probability, we actually just rearrange the multiplication rule that we've already seen. Two different versions are both valid. We can talk about the probability of A, conditional on event B, event B has happened, or the probability of B given that A has happened. In either case, in the numerator of our calculation of the probability, we'll have the probability of A and B. That is the intersection between the two. That is the area that is cross-hatched in both red and blue in my Venn diagram. For example, what I have in my Venn diagram is the probability of A conditional on B. Since I know that B has happened, the only way that A can happen is if it occurs within this cross-hatched area. However, the area in event B does not sum up to be equal to 1, so I have to normalize by dividing by the probability of B. Likewise, I could calculate the probability of B conditional on A having happened. I would have to take the same cross-hatched area, but in that case divide by the probability of A, or the area that's contained by the A circle. Again, an example will make this clear. What I'm going to do is take my pivot table and I'm going to calculate a conditional probability. I'm going to condition the choice of box on whether or not I find a defect. This will allow me to answer questions such as, hey, I just found a defective light bulb. What's the probability that it came from box Y, etc. In order to calculate this conditional probability, I'm going to have to use the marginal probability of finding a defect and no defect. I will then adjust each one of the joint probabilities by dividing by the marginal probability. This is according to the formula that we looked at 2 slides ago. So for example, we know that the probability of a defect, regardless of box, is equal to 0.31, and the probability of no defect, or the marginal probability of no defect, is equal to 0.69. Therefore, if I divide every column entry in the joint probability statement by 0.31, the probability of a defect, I'm going to have the conditional probability of box X, Y, and Z conditional on having found a defect. If I take each one of the entries that are in the second column and I divide them by 0.69, the probability of not finding a defect, then I have the conditional distribution of box X, Y, and Z choice conditional on not having found a defect. Now I can answer questions such as this. What is the probability that I have selected box Y if I know I have a defect? Clearly, looking at the table where I've carried out each one of the calculations, the probability is 16%. So if somebody hands me a defect, a light bulb, and they tell me it's defective, I know that I can adjust my probabilities and say now I believe there's a 16% chance that it came from box Y rather than the original 1/3 chance. Independent events. If the probability of one event isn't changed by the existence of the other events, then we say that the two events are independent of each other. So if two events A and B are independent, then the probability that A happens, conditional on B happening, is just equal to the marginal probability, or the probability of A. Knowing that event B happened gives me no additional information in predicting whether or not A will happen. The same needs to be true for event B. If A and B are independent, then the probability of B conditional on A is just the marginal probability. And knowing that event A happened gives me no information as to the probability of whether or not B will happen. The multiplication law for independent events is a simplified version of the multiplication law that we already covered. The multiplication law can also be used to test to see if two events are independent. If it is true that the two events are independent, then the probability of A and B simplifies to a simple product of marginal probabilities, the probability of A times the probability of B. This is an easy way to check for independent events in a contingency table. Here's our contingency table for box selection and defective and non-defective light bulbs. If it's true that box selection and defective and non-defective light bulbs are independent events, then each one of the entries in the joint probability part of the table should be the simple product of the marginal probabilities that are associated with those joint probabilities. For example, if it's true that these are independent events, then 0.13 should be equal to the product of the marginal probabilities 0.31 and 0.33. That must hold for every single entry in the joint probability table. This is an easy way to check for independence. For example, we have the probability of Z and its intersection with no defect. In other words, the probability of Z and no defect. That is equal to 0.21. Here is Z, and here is no defect. Now, if these are two independent events, then that 0.21 should be able to be calculated by taking the marginal probabilities and multiplying them by each other. In other words, taking 0.69 and multiplying that by 0.33. But when I do so, I get the answer of 0.23, and it's clear that 0.21 and 0.23 are not equal to each other. So these are not independent events. That should not come as a surprise to you, since you know that once we've selected the box, the probability of selecting a light bulb that's defective or non-defective is different depending on which box we've selected. Mutually exclusive events. Two events are said to be mutually exclusive if the events have no sample points in common. We draw this in a Venn diagram by drawing a circle for event A and a circle for event B and making sure that there's no overlap between the two circles. This simplifies the multiplication rule. Typically, with the multiplication rule, we have to subtract out the probability of A and B because we count the overlap twice. But in this case, the probability of A and B is equal to 0, and so there's no need to subtract it from the formula, and we get a formula which is the simple addition of the probability of A plus the probability of B. The only other thing I would like to mention is that you should not confuse the concept of mutual exclusion with the concept of independence. Clearly, if two events are mutually exclusive, they're highly dependent on each other. Students often get the two different concepts confused and think that if two events are mutually exclusive, they must be independent of each other. That's not true. Here, if event A occurs, then I know that event B cannot occur. And if I see that event B occurs, I know that event A cannot occur. That's a very strong form of dependence. Finally, I'm going to cover Bayes' theorem. Bayes' theorem is a way of taking subjective probabilities and updating them based on new information. We'll often begin our probability analysis with a subjective or prior probability. So another word for our subjective probability is our prior probability. Then we will collect some information from a sample, maybe a special report or a product test. And then given this information, we revise our posterior probabilities. Note that this is exactly what I did when I calculated my conditional probabilities. And I updated my information about what box an item came from based on knowledge about whether or not the item was defective or not defective. Bayes' theorem provides a popular formula that's used for revising prior probabilities. Here's the formula, which I know looks a little bit intimidating, but once we've applied it once, I think you will fully understand the application of Bayes' theorem. Bayes' theorem is applicable when the events for which we want to compute posterior probabilities are mutually exclusive and their union covers the entire sample space. Sometimes these are called partitions over the sample space. Here's a simple application. It's from one we're familiar with, our boxes and our defective and non-defective light bulbs. Here I've represented both the tree diagram and the contingency table or pivot table that I built for you from the tree diagram. Let's say that our prior probability that a part is from box X is equal to 33%. That seems to make sense since we're randomly selecting from 3 boxes. How do I modify this probability if I discover that the part is defective? Well, the answer really is nothing but a conditional probability. Using Bayes' theorem, I can calculate the conditional probability that it came from a particular box, which I labeled event A, conditional on event B, which is whether or not the light bulb that I found is defective. So here what we're looking at is the probability that A is equal to X given that B is equal to D, or defective. That's calculated according to Bayes' theorem by taking the probability of A and multiplying it by the probability of B given A. That is, the probability of selecting box A, or box X, which is equal to 1/3, times the probability of defective if I've selected box X, and we know that that's 2/5. That will constitute the numerator of our ratio as we apply Bayes' formula. In the denominator, what we conclude is the probability of defective given X times the probability of X, plus the probability of defective given box Y times the probability of selecting box Y, and then we'll add the probability of defective given box Z multiplied by the probability of picking box Z. Notice what we're really doing here is summing up all of these probabilities in order to calculate the probability overall of a defective item. That is in the numerator. In the denominator. So here's the application of Bayes' theorem. The probability of A given B, where A is the event that we pick box X, and that is conditional on having knowledge or having discovered that B is equal to defective. We take the 1/3, which is the probability of selecting box X. We multiply that by the probability of a defect if we've selected box X. That is our 2/5. We then take that 2/5, the probability of defective given box A, and multiply it by the probability of box A, is 1/3. That's this part of the formula, the first term in the denominator. Then we add the probability of getting a defect from box Y, which is 1/6, multiplied by 1/3, which is the probability of picking that box. And then finally, to complete the complement part of the formula, we take the probability of getting a defect from the third box, box C, and multiply it by the probability of selecting that box. This is, in essence, the probability of getting a defect. Carrying out the calculation, we find 0.42. So I would update my probability that the item came from box X based on knowledge that it's defective to 0.42, or 42%. So I would upgrade the probability or likelihood from 33% to 42%. Why do you think that's the case? Well, take a careful look at the tree diagram, and what you'll discover is that box X has a full 2/5 of its light bulbs which are defective, whereas box Y only has 1/6 of its light bulbs that are defective. So based on knowledge that it's defective, we would want to upgrade the probability that it came from box X, because overall, box X tends to have more defective light bulbs than the combination of boxes Y and Z together. An updated probability. Finally, we're going to just cover assigning probabilities to experimental outcomes, because this will be necessary for defining random variables and probability distributions of random variables. Random variables are defined over the events of the sample space. If we know the probabilities of the different events in the sample space, we can derive the probability distribution of the random variable. Here's the coin toss problem. If I toss a coin 2 times and I record heads and tails with each trial, I know that there are 4 possible outcomes. Heads, 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 tails, tails, heads, and tails, tails. In assigning probabilities, I might use the classical approach and assume that every time I flip a coin in an independent trial, there are 2 possible outcomes, and each outcome has a probability of 50%. Therefore, there are 2 times 2 equals 4 possible outcomes, and the probability of each one of those outcomes, using the product rule and given the independence of the 2 events, is simply the product of 0.5 times 0.5, or 0.25. So each one of the outcomes is equally likely, with a probability of 0.25, and of course 0.25 added up 4 times is equal to 1. So the 2 basic rules of assigning probability that we covered at the beginning of this presentation are satisfied.